Welcome back, junior associates. You've done the hard work. You've mastered the high-resolution Hubble power of the Ford ICR, and you've seen the benchtop efficiency of the Orbitrap. By now, you know how to weigh a molecule down to the 6th decimal place. But let's be honest with each other for a moment. Knowing the weight is only the beginning of the story. It's a data point, not a discovery. Today, we move beyond the surface. Welcome to Module 8-3, Tandem Power. Imagine you are a professional safecracker. You walk into a dimly lit room and see a massive, high-security vault. You put it on a scale, and it weighs exactly 500.4567 kilograms. Now, that's a great piece of data. It tells you it's a heavy-duty model. It tells you it's likely made of a certain grade of steel. But it doesn't tell you what's actually inside. It doesn't tell you if it's full of gold bars, stacks of cash, or a collection of vintage watches. To find the ultimate truth, you don't just need to weigh the safe. You need to blow the door open and see the jewels inside. In our world, the jewels are the molecular structure, the specific arrangement of atoms that defines the identity and function of the chemical. A single MS run is just the scale. It gives you the precursor ion, the weight of the safe. But the pro move is knowing how that molecule falls apart under pressure. Before we start cracking safes, we need to ground ourselves in the analytical logic of investigation. As a consultant, I'm often asked, if I have the exact mass, why do I need to break the molecule? The answer is simple: isomerism and structural complexity. Two completely different molecules can weigh exactly the same. The scale can't tell them apart, but their internal jewels are different. When we talk about tandem power, we are talking about a two-stage process. Stage 1 is the search, finding the precursor ion. Stage 2 is the interrogation, the fragmentation event. By analyzing the pieces that fly out when we shatter that safe, we can work backward to figure out how it was built. If you see a fragment that weighs 77, you likely had a benzene ring. If you see a loss of 18, you likely had water. This is the forensic mindset of a molecular detective. In my years of workflow optimization, I've found that understanding instrument architecture is the secret to analytical success. We have two fundamental concepts: Tandem-in-Space and Tandem-in-Time. Understanding this distinction is the analytical logic that separates the architects from the technicians. Think of Tandem-in-Space as a high-efficiency assembly line. You have different machines at different physical locations, each performing a specific task in a relentless sequence. Contrast that with Tandem-in-Time. This is the multi-purpose room. You stay in one place, usually a trap, and you perform your tasks in a sequence of timed events. You trap, you isolate, you shatter, and you measure. Your choice dictates your capabilities: assembly line efficiency versus forensic deep dive. The most famous example of Tandem-in-Space is the triple quadrupole, or QQQ. In the consulting world, we view the QQQ as the workhorse of quantitation. It operates exactly like an assembly line. In Machine 1, Q1, we perform selection, picking one specific safe from a crowd. In Machine 2, Q2, the collision cell, we blow the door open using gas. Finally, in Machine 3, Q3, we sort through the resulting jewels, product ions. Because the ions move in a straight line through separate physical components, the process is relentless and fast. It's perfect for targeted quantification, finding exactly what you are looking for in 10,000 different samples. Now let's look at the other side of the coin: Tandem-in-Time. This is your forensic deep dive. Instead of moving through different machines, the ions stay in one place, usually a trap. The strategic benefit here is something an assembly line simply cannot do: $MS:(N). Because the ions are still in the trap after the first break, we can pick one of those fragments, kick everything else out, and shatter that fragment again. We can do this 3, 4, or even 10 times. It's like a set of Russian nesting dolls. Every time you open one, there's a smaller, more detailed secret inside. In Tandem-in-Time, we trade speed for depth. We trade volume for analytical insight. Now let's get into the strategic configuration of your experiment. The first and most common mode is the product ion scan. Think of this as the molecular autopsy. You have found one specific body, your precursor ion, and you want to see every single thing it was made of. Here is the configuration. You lock Q1 onto one specific mass. Only that molecule gets through the gate. Then, in the collision cell, you shatter it. Finally, you set Q3 to full scan mode. Q3 sweeps across the entire range to see every single piece produced from that one parent. This is how you get your structural fingerprints. It filters out the noise and says, "Show me only what belongs to this safe." Sometimes, you aren't looking for one molecule, you're looking for a whole group. That brings us to the Precursor Ion Scan, the family search. Imagine you are a detective looking for everyone who carries a specific DNA fragment, maybe a specific sugar or phosphate group. We lock Q3 on that DNA and let Q1 scan for all possible parents. Then we have the neutral loss scan, the hunt for the missing piece. Some molecules lose a neutral piece, like water or $CO_2. Here, Q1 and Q3 dance together. They scan simultaneously, but Q3 is always behind Q1 by a fixed mass, say 18 Daltons. If Q1 sees a mass, and Q3 sees it -18 at the same time, you've found a molecule that lost water. It's a brilliant shortcut for identifying entire classes of compounds in a dirty matrix. Finally, we have selected reaction monitoring, or SRM, often called MRM when we target multiple compounds. In the world of high-stakes pharma, this is your high-speed radar. Unlike the other modes, we aren't scanning anything here. Both Q1 and Q3 are locked. Q1 stays on the parent. Q3 stays on one specific diagnostic child fragment. Think of the efficiency here. The instrument is staring intensely at one specific transition. Parent A becomes fragment B. This isn't for discovery. You already have to know what you are looking for. By ignoring everything else, the instrument becomes incredibly quiet and incredibly sensitive. It is the industry standard for drug quantification and clinical diagnostics. How do we actually blow the door open? We use physics. In most tandem instruments, we use collision-induced dissociation, or CID. After we select our precursor ion in Q1, we accelerate it into a collision cell filled with an inert gas, like nitrogen or argon. Here is the high-performance logic. We don't hit the molecule with one massive blow. Instead, every time the ion hits a gas atom, a tiny bit of its kinetic energy is converted into internal energy. The molecule starts to vibrate. If you give it enough nudges, the vibration becomes so intense that the weakest chemical bond simply snaps. Your goal as a strategist is to find the sweet spot, the exact amount of energy needed to break the molecule into meaningful pieces without turning the jewels into dust. Let's wrap up this high-level briefing on the strategy of the shatter. Today, we've learned that Tandem-in-Space is our assembly line for speed, while Tandem-in-Time is our multi-purpose room for deep investigation. We've mastered the 4 scan modes: the autopsy, the family search, the missing piece, and the high-speed radar. And we've understood that CID is the mechanism we use to vibrate a molecule until its truth is revealed. Here is my golden quote for your career growth. In Tandem MS, the debris is the data. Don't fear the fragmentation. Embrace it as the map to the structure. You should feel a sense of analytical logic now. You are no longer just weighing boxes. You are a molecular detective. But having the data is one thing. Solving the case is another. In our next unit, Module 8-4, we take these fragments and reconstruct the chemical puzzle from the ground up. I'll see you at the crime scene.